Hello everyone, we continue our course of lecture formal languages, automata and codes, and today our lecture will be devoted to the some type of automata. And first of all, I tell you that this lecture and other lecture you can find in my official website. Here. This time, here there are three lectures, and after recorded, you can find lecture number 4. So, okay, we shall start. First type of automaton we study is the detail of finite acceptors that are deterministic in their operation. We start with the precise formal definition of the deterministic acceptors. The following figure represent two single automata with some common features. So the first and the second. Both have a finite number of the terminal states. Both processes in input string consisting of the sequence of symbols. Both make transition from one state to another depending on the current state and the current input symbols. Both produce some output, but in the slightly different form. The automaton in the first figure only accept or reject the input. The automaton on the second figure generates an input string. Notice also that both automata have a single well-defined transition at each step. All of these filters are incorporated in the following definition. A deterministic finite acceptor, or shortly DFA, is defined by the quintuple M, which consists where Q is a finite set of internal states. The sigma is a finite set of symbols called the input alphabet. The delta from the product Q and sigma into Q is a total function called the transition function. Q0 from Q capital is the initial state. A subset F from the set of internal states Q capital is a set of final states. A deterministic finite acceptor operators is the following manner. As the initial time, it is assumed to be in an initial state Q0 with its input mechanism on the leftmost symbol of the input string. During each mode of the automaton, the input mechanism advances one position to the right, so each move consumes in one input symbol. When the end of the string is reached, the string is accepted of the automaton is in one of its final states. Otherwise, the string is rejected. The input mechanism can move only from left to right and reads exactly one symbol on each step. The transition from one internal state to another are governed by transition function delta. For example, if delta of Q0A is equal to Q1, then the deterministic finite acceptor is a state Q0 and the current input symbol is A. The DFA will be going into state Q1. In the discussing automata, it is essential to have a clear and intuitive picture to the work with. To visualize and represent finite automata, we use transition graphs, in which the vertices present state and the edges present transitions. The label on the vertices are named of the states, while the label on the edges are current values of the input symbol. For example, if Q0 and Q1 are internal states of some deterministic finite acceptor M, then the graph associated with M will have one vertex labeled Q0 and another labeled by Q1. And HQ0, Q1 labeled represents the transition Q, which is labeled by the symbol A, yeah? Represents the transition Q, delta of Q0 A is equal to Q1. The neutral state will be identified by an incoming unlabeled arrow not originating at any vertex. Final states are drawn with a double cycle. More formally, if M Q sigma delta Q0F is a deterministic finite acceptor, then its associated transition graph GM has exactly cipher of Q vertices, each one labeled with a different QI from Q capital. For every transition rule, delta of QI A is equal to QG. The graph has an edge QI/QG labeled by a symbol A. The vertex associated with the Q0 is called the initial vertex, while those labeled with QF belongs to F capital are the final vertices. It is a trivial matter to convert from the Q sigma delta Q0F definition of the deterministic finite acceptor to its transition graph representation and vice versa. Example: the graph in the following figure represents a deterministic finite acceptor M, which consists of all states are Q0, Q1, Q2. Yeah, the alphabet is 0 and 1. The transition function is delta. The neutral state is Q0, and the terminal or output state is Q1. Where the transition function delta is given by the following way: Q of delta of Q0 0 is equal to Q0, delta of Q1 0 is equal to Q0, delta of Q2 0 is equal to Q2, delta of Q0 1 is equal to Q1, delta of Q1 1 is equal Q, delta of Q2 1 is equal Q1. This deterministic finite acceptor accepts the string 0, 1. Starting in the state Q1, the symbol 0 is read first. Looking at the edge of the graph, we see that the automaton remains in the state Q0. Next, the symbol 1 is read and the automaton goes to the state Q1. We are now at the end of the string and at the some time in the final state Q1. Therefore, the string 0, 1 is accepted. The deterministic finite acceptor does not accept the string 0, 0 because after reading two consecutive zeros, it will be a state Q0. By similar reasoning, we see that the automaton will accept the string 101, 0111 and 11001, but not 100 or 1100. It is convenient to introduce the extended transition function delta star from the product Q and sigma star into Q. The second argument of delta star is a string rather than a single symbol, and its value gives a state the automaton will be in after reading that string. For example, if delta of 0A is equal Q1 and delta of Q1B is equal Q2, then delta star of Q0AB is equal Q2. Formally, we define the transition function delta star recursively by the formula. The first formula, delta star of Q lambda is equal to Q, delta star of QWA is equal to delta of delta star QV of A for all Q from Q capital for any string from sigma star and any symbol A from sigma. To see why this is appropriate, let us apply this definition to the single case above. First, we use formula 2 to get that sigma star of Q0 AB is equal to sigma, delta star of QI AB is equal delta of delta star Q0A and B. But delta star of Q0A is equal to delta of delta star of Q0 empty word lambda, of A is equal delta of Q0A is equal Q1. Substituting this into the formula 3, we get the delta star of Q0AB is equal delta of Q1B is equal Q2, as expected. Having made a precise definition of acceptor, we are now ready to define formally what we mean by the associated language. This association is obvious. The language is the set of all strings accepted by the automaton. Definition: the language accepted by deterministic finite acceptor M is the set of all strings on the sigma accepted by M. In formal notation, the language accepted by the DFAM consists of such words that the deterministic the transition function delta star of Q0 of W belongs to F. We know that requires that transition function delta and consequently the transition function delta star will be a total function. At each step, a unique mode is defined, so that we are justified in calling such an automaton deterministic. And deterministic finite acceptor will process every string in sigma star and either accept or not accept it. Non-acceptance means that the deterministic finite acceptor stop in as a non-final state, so that the complement of the language which accepts the deterministic automaton M consists of the sub string from the sigma star such that delta star of Q0W not belongs to F. Example. Consider the deterministic finite acceptor in the following figure. In the drawing, we allow the use of two labels on the single edge. Such multiply labeled edges are shorthand for two or more distinct transitions. The transition is taken whenever the input symbol matches any of the edge label. The automaton in the figure remains in its initial state Q0 until the first B is encountered. If is also as the last symbol of the input, then the string is accepted. If not, the deterministic finite acceptor goes into state G2, from which we can never escape. The state Q2 is a trap state. We see clearly from the graph that the automaton accepts all strings consisting of an arbitrary number of A's, followed by a single B. All other input strings are rejected. In the segmentation, the language accepted by the automaton is L, which consists of the string of the from A in power and B, where N is a non-negative integer. This example shows how the convenient transition graph are for working with the finite automata. While it is possible to base all argument strictly on the properties of the transition function and its extension through formula 1 and 2, the results are hard to follow. In our discussion, we use graphs which are more intuitive as far as possible. To do so, we must, of course, have some assurance that we are not misled by the representation and that argument based on the graphs are as valid as those that use a formal property of the transition function delta. The following preliminary result gives us this assurance. Theorem. Let M be a deterministic finite acceptor and let Gm be its associated transition graph. Then for every Qi, Q, G state of this automata and any string from W from sigma plus, delta star of QIV is equal to QG if and only if there exists in the graph GM a value with the level W from the vertex QI to QJ. The proof. This claim is very obvious from the examination of such simple case as in example 2.1. It can be proved rigorously using the induction of the length of the string W. Assume that the claim is true for all strings V with length less or equal n. Consider when any string W of the length n plus 1 and write is as W is equal VA. Suppose now that delta star of QIV is equal QK. Since the length of the word V is equal N, there must be a walk in the graph GM labeled by V from vertex from QI to QK. But if delta star of QI is equal QJ, then deterministic finite acceptor M must have a transition delta of QKA is equal to QJ. So that by construction of the graph GM has an H Q K QJ with the label A. Thus, there exists a walk in the graph GM labeled by the string VA, which is equal W between vertices QA and QJ. Since the result is always true for n is equal 1, we can claim by induction that for every string from W from sigma plus, we have that delta star of QA W is equal to QG. It implies that there exists a walk in the graph QM from the vertices QI to vertices QG labeled by the string W. The argument can be turned around the straightforward way to show that the existence of the such a path implies formula 4. This completes the proof of the theorem. Again, the result of the theorem is so intuitively obvious that a formal proof seems unnecessary. We went through the data of 2 reasons. The first is that it is a simple yet typical example of the intuitive proof in connection with automata. The second is the result will be used our and our. So stating and proving it is a theorem lets us argue quite confidently using graphs. This make our example and proofs more transparent that they will be if we used the property of the transition function delta star. While graphs are convenient to visualization automata, other representations are also useful. For example, we can represent the function delta as a table. The table in the figure equivalent to the following figure. Here, the row label is the current state. While the column label represents the current input symbol. Yeah. The entry in this table defines the next states. It is apparent from the example that the deterministic finite acceptor can be easily be implemented as a computer program. For example, as a simple table lookup or as a sequence of its statements. The best implementation of representation depends on the specific application. Transition graphs are very convenient for the kind of argument we want to make here. So we use them at most of our discussion. In constructing automata for the learning definitely informally, we employ reasoning similar to that for programming in high-level languages. But the programming of the deterministic finite acceptor is tedious and sometimes conceptually complicated by the fact that such an automaton has a few powerful features. Example. Find a deterministic finite acceptor that recognizes the set of all strings on the alphabet sigma, which consists two letter A and B starting with the prefix AB. The only use here is the first two symbol in the string after they have been read. No further decision are needed. Still, the automaton has been processed in the whole string before the decision is made. We can therefore solve the problem with the automaton that has 4 states: an initial state, 2 states for recognizing string A, B, ending in the final trap state, and 1 non-final trap state. In the first symbol is the letter A and the second is the letter B. The automaton goes to the final step trap state, where it will be stay things. The rest of the input goes does not matter. On the other hand, if the first symbol is not the letter A or the second is not the letter B, the automaton enters the non-final trap state. This simple solution is shown in the following figure. Here input state, here the trap state or out state here, output state. The next example. Find the deterministic finite acceptor that accept the string on the alphabet 01, except those constituting the substring 001. In the decision whether the substring 001 has occurred, we need to know not only the current input symbol, but we also need to remember whether or not it has been preceded by 1 or 2 zeros. We can keep a track of this by putting the automaton into specific state and label them accordingly. Like variable names is a programming language. The state names are arbitrary and can be chosen by mnemonic reasons. For example, the state in which 2 zeros were in the immediately preceding symbol can be labeled simply 00. In the string starting with 001, then it must be rejected. This implies that there must be a part labeled 001 from the initial state to a non-final state. For convenience, this non-final state is labeled 001. This state must be a trap state, because later symbols do not matter. All other states are accepted states. This gives us the basic structure of the solution, but we still must be add provision for the substring 001 occurring into the middle of the input. We must define states Q capital and transition points delta, so that whatever to need to make the correct decision is remembered by the automaton. In this case, when the symbol is read, we need to know some part of the string to the left. For example, whether or not the 2 previous symbols were 00. If we label the state with the relevant symbol, it is very easy to see that the transition must be, for example, delta of 00 and 0 is equal to 00. because this situation arises only if there are three consecutive zeros. We are only interested in the last two. In fact, we remember by keeping the deterministic finite acceptor in the state 0, 0. A complete solution is shown in the following figure. We can see from this example how useful mnemonic labels on the state are for keeping track of things. Trace a few strings such as 100, 100, and 1010, 100. See that the solution is indeed correct. Every finite automaton accepts some language. If we consider all possible finite automata, we get a set of languages associated with them. We shall call such a set of languages a family. The family of languages that is accepted by the deterministic finite acceptor is quite limited. The structure and property of the languages in this family will become clearer as our study proceeds. For the moment, we shall simply attach a name to this family. Definition: language L is called regular if and only if there exists some deterministic finite acceptor M such that L is the recognized language of this DFAM. Example: show that the language L, which consists of words which start with A and finish by the symbol A, is regular. To show that this or any other language is regular, all we have to do is find a deterministic finite acceptor for it. The construction of diff A for this language is similar to the example 203, but a little more complicated. What this deterministic finite acceptor must do is check whether a string begins and ends with the letter I. What is between is immaterial. The solution is complicated by the fact that there exists no explicit way to testing of the end of the string. This difficulty is overcome by simply putting the deterministic finite acceptor into a final state whenever the second A is encountered. If this is not the end of the string and another B is found, it will be take the deterministic finite acceptor out of the final state. Scanning continues in this way, each of taking the automaton back to its final states. The complete solution is shown in the following figure. Again, trace a few examples to see why this works. After one or two tests, it will be revealed that the deterministic finite acceptor accepts a string if and only if it begins and ends with the letter A. Since we have constructed a deterministic finite acceptor for the language, we can claim that by definition the language is regular. The next example. Let S be the language in the previous example here. Shows that the language L square is regular. Again, we show that the language is regular by constructing of the deterministic finite acceptor for it. We can write an explicit expression for the language L square, namely L square consists of such word which start with A, next will be any word W, then we have AA and any word from alphabet AB, and this word ends by the symbol A. So the automaton which recognizes language will be the following. Therefore, we need a deterministic acceptor that recognizes two consecutive strings of the essentially of the same form, but not necessarily identical in the value. The diagram in the figure of the example 2.5 can be used as the starting point. But the vertex Q3 has to be modified. Here, automaton from the example 2.5. The state can be longer, be final, because at this point we must start to look for the second substring of the form AWA. To recognize the second substring, we replicate the state of the first part. View new names with the Q3 as the beginning of the second part. Hence, the complete string can be broken into its constituent part whenever AA occurs. We let the first occurrence of two consecutive A's be the trigger that gets the automaton into the second part. We can do it by making that delta of Q3A is equal to Q4. The complement solution is the figure below, yeah, which also this graph or automaton was represented at the start of our example. This deterministic finite automaton accepts the language L square, which is therefore regular. The last example suggests that the conjecture that if the language L is irregular, so are L to L, L in power 2, L in power 3, and so on. We shall see later that this is indeed correct. So we finish our lecture. I wish you good luck, good health, and to finish our war with Russia. And goodbye.